Hello all, I welcome you all to the 13th lecture and the first lecture after the mid-sem examination. I hope you all had a very good mid-semester recess, and we will start with a very short recap of what we have been doing till now. I will bring us up to speed, and for the first part of this week we will talk about thermodynamics and statistics of particles. This is important because we will very quickly derive the electron statistics uh, at any non-zero temperature. Till now, we have been talking about electrons in semiconductors at 0 Kelvin. Though we have used the fact that the electrons have uh, non-integer or semi-integer spins, half and minus half spins, and phonons and other particles which are called bosons have integer spins. And because of the fact that they have integer and non-integer spins, the statistics are different, and they are governed by different population distributions. So we will see the background of that, and then we will introduce spins, the effect of spin orbit coupling in band structures, and we will continue to discuss regarding novel sub nano or sub micron structures, quantum wells, and so on. So without much ado, let's do a recap of what we have been doing till now. So we will say first half recap. Okay, so we started with understanding electron transport in metals and semiconductors. We came up with all materials are made up of atoms. These were identified by chemical reactions and the fact that very few of the molecules are stable, and each atoms are once again can be subdivided. Atoms have protons, neutrons, and electrons. The individual masses of these things were known by specific experiments, and in terms of electrons, we knew much about what is called as valence electrons. Even before we understood about bands and how electrons occupy in an atom, there are certain experiments particularly about why certain chemical bonds were formed. We always knew about, or empirically we know about, how many valence electrons each or many atoms have. For instance, we knew that the most stable oxides of copper is copper cuprite and cuprates, right? Cu2O and CuO. And we know what sodium forms. We know sodium hydroxide and sodium chloride. We know how silicon forms its oxide. We know how aluminum forms its oxide, and what are the atomic ratios and such. So from there we know what are the valence electrons. Once we have valence electrons, we knew about electric current and fields. We know that empirically the electric current density J was found to be linearly variant with the electric field. The proportionality constant is called as the conductivity. Now we went ahead and then we showed that electrical conductivity and thermal conductivity are related in most metals. We found that the ratio of sigma by kappa was always a constant and depends only on temperature. And the model to describe electric current and thermal conductivity in the metal was provided by Drude. We saw this in many places. The Drude's model we saw in 614, and we also derived the Drude's model in some length even in 698 m. We treated all the valence electrons in the metal to be like atoms in an ideal gas. We showed that the current density, which can be written as the number of electrons times the velocity, can be calculated. The velocity was estimated by assuming there exists what is called as tau, which is called as a relaxation time. So if we take an electron at random, what is the mean time at which it will scatter can be defined by relaxation time tau. If we know tau and m being the mass of the electron, we can estimate the conductivity sigma to be Ne squared tau by m times E, and this is our famous Ohm's law. While it has a lot of very good results, it was able to explain the ratio of electrical conductivity to thermal conductivity and such. There were some shortcomings. The mean free path extracted from the relaxation time, lambda, was always found to be close to the interatomic distance, and which was experimentally known to be not true, because the mean free path in most of the metals at very low temperatures can reach a few microns, which are multiple atom distances, right? And also the temperature dependent of conductivity could not be well explained by the Drude's model. Now, to understand the shortcomings of the Drude's model, we had to go to what is called as the wave nature of electrons. The biggest problem with the Drude is the assumption of the velocity. The velocity was taken to be determined by the thermal velocity or by the equipartition theorem, which tells you the thermal energy gives you the velocity in each direction, and given some degree of freedom, you can estimate what is the velocity. But then that has to change, because by the time Drude's model came out, there has been a lot of discussion about the various properties of electrons, and the electrons were shown to have some wave-like property. There are few properties of a wave, which is the energy E, the wave vector energy E, the wave vector k, and the wavelength lambda, right? And we know what are the relations for this. The simplest wave can be written as psi, which is called as a wave function. It determines how the wave varies in space and time. Is basically r comma t is written as a e power I k dot r minus omega t. K is called as the wave vector, r is any spatial coordinate, omega being the temporal frequency, and t being the time. With all these things, we knew that the momentum of such wave is given by h bar k, k being the wave vector. H is called as the reduced Planck's constant, which is h by 2 pi. The k wave vector is called as the spatial frequency, wave vector or spatial frequency. We showed that it cannot be continuous because there is some smallest value of k that can exist. There are different ways to see this. This is established by what is called as the von Karman boundary condition. The simplest way to look at it is we take a sample, some three-dimensional sample. The largest wave which can be fit into this sample should begin and end at the sample edges, right? If it does not begin and end at the sample edges, then there are going to be reflections. Or the other way to say is it has to have the same amplitude at the beginning and the ending. If such conditions are established, the smallest k that you can have will turn out to be 2 pi by Lx, kx along the x direction, or the wavelength will be the length of the sample along x, length of sample along y, length of the sample along z, right? So, and del ky is 2 pi by Lx. So this is called as the von Karman boundary condition, which gives you the smallest value of k or the largest wavelength that you can have in this sample. And once k vectors are shown to be not continuous and discrete, because there exists some smallest jump that you can have, for any given volume V, if we take it for simplicity as Lx into Ly into Lz, we have taken a cuboid, right? So the total volume to be something like this. The smallest volume of K in K space will turn out to be 8 pi cube by V, V being the volume in the real space. And if there exists, let's say, n number of valence electrons in a material, the last occupied K value is called as Kf, or the Fermi wave vector, is given by Kf is 3 pi cube n to the power 1 by 3. Right? This is for the three-dimensional case. There are certain things that one needs to appreciate here. So in K space, let's say this is Kx, Ky, and Kz, and we point, let's say, some value Kf and some sphere right around this. So what we mean is all possible cuboids that you can have here can have at max 2 electrons, right? So each electron can have spin up and spin down, which have the same energy, because the energy is determined only by the other 3 quantum numbers in an atom, as we saw previously. The spins mostly are degenerate, but then you can have 2 such spins. That's the Pauli's exclusion principle, right? And that gives you how many electrons you can fit in particular space. The Pauli's exclusion principle also gives you the fact that not all the electrons can now localize into one particular K value, that is the smallest K value. And because of this conflict, they start occupying higher and higher K spaces, K values, right? Now, let's take some electron density n in a typical metal turns out to be something of the order of 10 power 22 per centimeter cube. Then Kf will is something of the order of 10 power 9 1 by centimeter, and the momentum or the Fermi velocity can be given by h cross Kf by m, m being the mass of the electron, will turn to be something of the order of 10 power 8 centimeter per second. One has to contrast this Fermi wave vector or Fermi velocity with the thermal velocity at temperature 3 is equal to 300 Kelvin. If you say that the mass of the electron is 9.31 × minus 31, one can calculate the velocity, thermal velocity, which turns out to be of the lower 10 power 7 centimeter per second. So there is an order of magnitude difference in the velocity determined by the thermal energy and the velocity obtained from the Fermi wave vector description. Right? This is because of the fact that you can have only so many density of K values given particular distribution, and you cannot have all the electrons in the same K value. Right? So that gives you a velocity in the, at least the topmost electrons have velocity of the order of 10 power 8 centimeters per second, whereas the maximum velocity at any given temperature, even at 300 Kelvin. So this is even at 0 Kelvin, right? At 0 Kelvin, the thermal velocity is almost 0. So what we are saying is, if we take any semiconductor or any metal, even at 0 Kelvin, the topmost electrons have a velocity of 10 power 8 centimeter per second, right? Which is not even close to the, which actually, okay, so it makes sense to even compare that, right? So this is 0 Kelvin velocity. And the 0 Kelvin velocity Vf is order of about 10 to the power 4 Kelvin. That is the thermal velocity at 10 power 4 Kelvin, right? So the electrons and the topmost energy level or at the Fermi level behave as if its temperature is about 10 power 4 Kelvin. Remember, the room temperature is about 300 Kelvin, right? So this is the difference between the actual electronic behavior in a material and what Drude has assumed. The very fact that the velocities are an order of magnitude already tells you that the mean scattering length is going to be much larger than what Drude has predicted. So we are already closer to the reality, right? So now After this, we spoke about electrons as in waves, and then we showed that the waves in quantum mechanics have to satisfy what is called as the Schrodinger's equation. We can derive this. We cannot actually derive from first principles, but we can look at it from several ways. We saw it in one particular way. What we did is, if psi is some wave function, that is some spatial description and the temporal description of a wave, which can be written as psi of r comma t is some a e power ikx ik dot r minus omega t. It obeys what is called as if I take IH bar dou by dou t and if acts on psi, it gives us h cross omega into psi again. So this is an operator, and this is a function, right? So this is called as a wave function, and this differential operator in mathematical term is called as an operator, is an energy operator. One with a hat is an energy operator, and because this operator acts on psi and gives you back psi, this equation is called as an eigen equation. Right? And this h cross nu is a constant which is called as an eigenvalue. Right? So we can write this particular part as E hat psi acting on E being a real number into psi. So this is one part of the Schrodinger's equation. We also saw another operator H, which is called as the Hamiltonian, has two parts. One is the kinetic energy, which is p square by 2m, again an operator, plus v. V is the potential energy which is dependent on the spatial coordinates. The momentum depends upon the mass and the velocity, and the potential depends mostly on only the position. Right? So the total description is given by the Hamiltonian H hat. And the Hamiltonian from classical mechanics, if it acts on psi, the wave function, should again give you E, which is the energy, because Hamiltonian is a total energy, E times psi. So since both the right hand side of these two equations are the same, one writes H hat psi is E hat psi. So this is the famous Schrodinger's equation. We found solutions of the Schrodinger's equation for several potentials V, the simplest being the free electron potential, and under free electron case where V equal to 0, we find the solutions for psi as plane waves. In one dimension it is written as a e power ikx, and in three dimensions it is e power ik dot r. And obviously we know that electron energy is h cross nu, and nu can be written as E by h prime, and the time component of this solution is written as a e power minus or ikx into e power minus I E by h prime into t. And if we have some solution psi for a wave vector k, and we have another solution psi k prime, which is given by a e power I k prime x, if both of these guys, psi and psi prime, are solutions to the Hamiltonian, we know that because the Hamiltonian H is Hermitian, all the solutions having different eigenvalues have to be orthonormal. So we define an inner product psi k prime, psi should be equal to 0, because these two are solutions to the Schrodinger equation having distinct eigenvalues, right? So what we mean by this is we integrate psi k prime star psi dr equal to 0. This is also called as the overlap integral, right? Now these two, if you do this multiplication, gives you 0, means that the overlap is 0, the net overlap is 0, right? That's what tells you that these two are orthogonal. Another way to write this is delta of k prime minus k, which tells you that in the event k equal to k prime, the value of this integral turns out to be 1. This is the normalization criteria, and one can estimate what should be a if this is to be true, right? Now, in addition to this free electron condition, we also saw an electron in a potential well, infinite potential well. It can also be called as a square wall potential. Under these cases, we found the solution to behave something like have a form of a sine n pi x by a, right? So if we have an infinite potential well, something like this, we found the ground state which should not have any node. The first state will have a node, and the higher and higher states will have increasing number of nodes in the wave function, right? And we saw the example of an harmonic oscillator, but apart from it, we also saw the example of an electron in an spherically symmetric potential, or particularly spherically symmetric Coulombic potential. Electron in spherically symmetric Coulomb potential. This is basically the hydrogen atom, right? Under this situation, we also saw what should be the solution. It turns out to have some radial component, a constant e power minus rho by 2. Rho is a function of the radius. Rho power L is one of the quantum numbers, Lagrangian polynomials, n minus L minus 1, 2L plus 1. L is obviously an integer, and the spherical harmonics, L, M, theta, comma, psi. So we saw how these guys will form. We saw there are certain conditions between L, M, and N. Of course, these are the things for you to go back and look at, right? Now that we saw, finally we also saw what happens to an electron in a Dirac potential, but it's fine. I think you can go back and see. So quite after this, we started to look at electrons in periodic structures, because that's where we wanted to finally get at. We saw that if there exists, let's say, a series of atoms which has some translational invariance, for instance, this separation is, let's say, R, and you have a potential something like this. Of course, this is some infinite numbers, okay, so I am just drawing it for convenience like this here. The potential, if the atom is isolated, should be like these dotted lines, but because of the fact that two atoms are closer, you will have some interaction at this point, so the potential will now change something like this. So when we have a periodic lattice, we derived what is called as the Blocks Theorem. There are two ways to write this. The first one we wrote as psi k of small r plus capital R should be e power I k dot capital R psi k of R. In the MidSem examinations, many of you have had an issue with this particular simple equation. So if we have a wave function k with a wave function psi with a wave vector k which solves the Schrodinger's equation at any point r, right? What we mean by this block equation is the solution at any lattice translations psi of small r plus capital R is just a phase shifted value of this particular solution at small r. Right? This is what it means. The other way to write this is you write psi k of R is u k of R e power I k dot R. Right? E power I k dot R are plane waves. U k of R is some modulator, right? Some function which modulates, and there is a property that uk of r should satisfy for a wave function psi k of r to be periodic in a periodic potential. So we showed that uk of r should also have the lattice periodicity. What we mean is uk of small r plus capital R should be equal to uk of small r, right? And if uk of r has some has the periodicity of the lattice, you can write this as a Fourier series, so which can be written as some g, the reciprocal lattice, ug e power I g dot r, right? So this is the Fourier expansion of this one. So you can actually substitute this. So basically psi k of r will be summation ug e power I g minus k dot r, right? So this is summation of all g's. All right, this is the block solutions. Now from here we went ahead to find the solutions for electron and periodic lattice. There are two different ways to find it. The first one is called as nearly free electron model. In this model, we assume that the electrons are still free, right? They behave as if the periodic potential is not there. So what we mean is, let's say the periodic potentials as we saw previously are something like this, right? So we have a periodic arrangement of atoms. And we are talking about an electron energy level somewhere here, right? So it sees this periodic potential, but in most cases the electron wave function psi is almost equal to e power I k dot r. It's almost a plane wave, right? So the unperturbed solutions psi k naught and psi k prime is written as e power I k prime dot r. These are the two plane waves. And the Hamiltonian in the periodic case can be written as the free electron Hamiltonian plus some del h, which is a small value which is called as perturbation, right? So what we mean is the potential, when the potential is 0, we have the plane wave solutions. Now we take the plane wave solutions and treat the periodic potential as a very small perturbation to the unperturbed Hamiltonian h. Right? So h naught is the unperturbed Hamiltonian, which basically has p square by 2m plus v equal to 0 plus del h, whatever the periodic potential that we have here, right? And this del h is obviously a periodic perturbation, so it can be written in Fourier expansion as we saw previously. So del h can be written as summation over g ug e power I g dot r, right? Now we solve this this entire model in perturbation way. You can go back and look at these lectures. We will just tell you what are the final consequences when we solve this using perturbation theory, right? So what we saw is the probability for an electron with wave vector k to be scattered to another electron with a scattered along the wave vector k prime should satisfy two conditions. The first condition, energy of k should be very close to the energy of k prime. Only then the scattering is possible. And the second, k prime should be lattice constant separated from k. So it should be k plus g. G is a reciprocal lattice vector, and your k prime should be offset from k by one reciprocal lattice vector, right? Given these two conditions, we showed that in the Brillouin zone we have our free electron dispersion something like this. Electrons with k value, very small k value, something here, does not get largely scattered from this very small weak periodic potential. for k values very close to the brilliant zone, that is 2 pi by pi by a, right? 2 pi by a into 2, so basically it turns out to be pi by a. So when k vectors are close to pi by a, then it's easy to see that this can be scattered back to minus pi by a, and now the separation is basically 2 pi by a, which is one reciprocal lattice vector. So something here can be scattered back along this direction, right? And only under such conditions the scattering from the weak periodic potential is most probable. This is what we see from the perturbation theory. And when the electron k vector is 2 pi by a, you form what is called as standing waves. You form two sorts of standing waves. One is psi plus, which is given by e power I pi x by a plus e power minus I pi x by a. The second one is psi minus is e power I pi x by a minus e power minus I pi x by a. So these two forms two different energy levels, and the separation between these two is basically 2 UG, UG being the Fourier component of this expansion, right? Yeah. So with this you can also go down and then you will get back the usual Crony-Penning model, but I will not do that here. Finally, we will stop with a treatment on tight binding. So in the first case, when we solve the nearly free electron model, we are looking at electron energy levels far from the periodic lattice potentials, right? So something which has this difference. The second approach is called as a tight binding model. Which goes under the assumption that the electron wave functions are strongly influenced by the atomic wave functions. Basically, if you have a periodic lattice like this, we are talking about electron energy levels somewhere here, very close to the atomic core, right? So in the when we solve the atomic problem, we saw that you have 1s, 2s, 2p, 3s, 3p, 3d, and so on and so forth, right? Depending upon the L, M, and N values. So the solution for an electron, so this is energy, right? This energy can have several values. Okay, so let's actually, maybe it's good to describe it a little bit in more detail. So let's take a look at one isolated atom, right? And we saw that you have, let's say, 1s state here, 2s, let's say 2p, right, 3s, 3p, and so on. So you have several such atomic states, and when you bring many such another atom with similar number of states together, right, something of this sort, remember you will have all these things here also, right? Now we are talking about electrons which are not localized in an atom, but we are now talking about electrons which pervade through the entire crystal. So we are talking about something maybe here, oops, right, I'm going to break this here. So now I'm talking about an electron energies which are like this, which goes everywhere in the crystal, right? And the question is, what will be these energy levels? The solution for this, according to tight binding, is that you can find the solution of electron wave vectors. They are written as summation of atomic orbitals. Psi is, let's say, are atomic orbitals, and Bn's are some constants, right? And this Bn determine whether those atomic orbitals contribute to the electron wave functions. Psi A can be, let's say, 1s, 2s, 2p, so on. So if I say that the electron wave functions have contributions only from 1s, then this psi k is actually written as just psi s, psi 1s. If I say that the electron wave function has contributions from 2s and 2p, then psi k is written as psi 2s, so b1, b2, psi 2p, right? So the more the contributions you have, the more terms that you will have in these things. But when we went ahead and then solved the problem of tight binding, once again we came up with some conclusions. We came up with some selection criteria to tell you that not all possible combinations of atomic orbitals are feasible. And then we found that there are some selection criteria which tells you only certain atomic orbitals contribute. Once this is given, we came up with some conclusions for tight binding calculations. Once you fit this into the Schrodinger's equation, we'll come up with some conclusions for tight binding. The first one being that what all orbitals contribute to the electron wave function psi k is determined by the atomic overlap. So atomic overlap determines the contributions of atomic wave functions to the electron wave function. Electron wave function, here we mean the electron wave function of, or the delocalized electron wave function in the lattice. So in this, if the overlap is small, in the case of atomic orbitals which are very close to the core, like 1s orbitals, then the energy very close to the atomic orbitals will only contribute, in the sense that for at very low energies only the 1s orbital contribute. There will be no mixing with any other state. So for instance, only the lowest s state contribute, which means for 1s state there is no mixing, there is no overlap between them. So the atomic wave function of 1s is the same as the electron wave function at such low energies. Okay. If the overlap is large, atomic wave function overlap. So what do we mean by small and large is when we start moving the atoms closer, right? So basically we had one atom like this with, let's say, first wave function, the second wave function which looks like this, right? So this is px, let's say, and this is py, something of this sort, and we bring the other one close by. The 1s does not largely interact, but let's say the px interacts, right? Depending upon the interaction intensity or the integral of the interaction, you will start to include more and more atomic orbitals. So if the overlap integral is large, then the electron wave functions have contributions from several atomic orbitals. So this is what we called as electron hybridization. We have sp2, sp3 sort of hybridization, right? So the electron hybridization happens if the atomic wave functions overlap. right? So these were the solutions that we brought out using tight binding approximation. So even with the tight binding approximation, you can actually show that you will have bands and band gaps, because the overlap does not happen for all atomic energies. Only for certain atomic energies the bands overlap and the bands start to split, right? Because of the perturbation interaction. The second order perturbation tells you that the energy levels which are lower gets a little bit lower. The energy levels which are slightly higher before the perturbation starts get pushed even higher. So this will start to give you separation in energy levels as these atoms interact. This will start forming bands and band gaps, right? So this is where we stopped before the MidSem. And from the next lecture we'll talk about the thermodynamics and the statistics of electrons in semiconductors and metals.